When we utilize the Smith chart to perform shunt stub matching circuits, the key is that we don't actually ever have to calculate admittances. Admittances are pretty easily found via graphical techniques using the Smith chart, and to do that on a Smith chart, all you have to do is rotate 180 degrees on the operating circle. So you normalize your load impedance, as we've shown in a variety of examples now. You draw your operating circle centered at the origin of the Smith chart. Then what you do is you just draw a straight line from the normalized impedance point through the center of the Smith chart, and you make sure that that line extends to the other side of the operating circle. And where that, and what I've drawn here, that dotted line, where it intersects with the operating circle is your admittance point for the load. So to calculate admittances on a Smith chart, what you're actually doing is you're rotating 180 degrees on the operating circle. So I've got a little example here. We've got a load impedance that is 2 plus J1, so you can see I've plotted 2 plus J1 right here. And if I were to do the calculations of admittance, I would just divide 1 divided by 2 plus J1. You can throw that in your calculators and verify that it's 0.4 minus J.2. Well, if you rotate 180 degrees on the operating circle, what you see is that we've got this point right here, and we don't have a 0.4 circle here, but if we did, we'd see that the 0.4 circle intersects with the minus J.2 circle right there at that point. So to calculate normalized admittances, all we have to do on the Smith chart is rotate 180 degrees. The process for performing shunt stub calculations is pretty similar to the series stub calculations that we demonstrated earlier. However, we'll be working with the Smith chart on what's called an admittance basis instead. And just remember that admittance Y is equal to 1 over Z, and that is equal to the normalized conductance plus J times the normalized susceptance. So this is related to resistance, and this is related to reactance. They're not exactly the same because, R does not equal 1 over G, and X does not equal 1 over B. Instead, we know the relationship is Y equals 1 over Z. So these don't hold, but resistance and conductance are related, and susceptance and reactance are related. And we'll be operating the Smith chart on this basis instead, which we call the admittance basis. So just keep that in mind. It sounds more complicated than it really is. So the process, if we go through it, the first is that we use the Smith chart on an impedance basis, and we locate the normalized load impedance. We then draw our operating circle, and we rotate 180 degrees on the operating circle to find YL prime. We also find the 2 points where the operating circle crosses what is called the Y equals 1 circle. That's exactly the same as the R equals 1 circle. It's the same circle. We just give it a different name in the admittance basis. So at either of these admittance points, if we insert the appropriate susceptance value, will move us to the center of the Smith chart. So we're just trying to cancel out this susceptance value. So that takes 2 steps. The first is to measure the distance of rotation along the operating circle. This is, again, D. It's the distance of the stub from the load in terms of lambda. So we just find out how far along the operating circle we had to rotate to get to the intersection with the Y equals 1 circle. And the second step is that we need to calculate this B. We need to cancel out this B prime value by inserting minus B prime. And so we eliminate B prime just by canceling it out with its opposite value. And this is done in 2 ways, either with a short stub or an open stub. And if we add a short stub, we just need to figure out its length by measuring the value of rotation to this point minus B prime from the Y equals infinity point, or the short circuit point. And if we decide to use an open stub, if we want to calculate its length, what we have to do is we have to measure the distance from the open circuit point from the open circuit point, which is y equals 0, to this point minus b prime. So, and then we just insert the stubs, either open or short, of length, which was calculated by that rotation. And like everything else in these video sections, I just feel like shunt stub calculations are best understood via an example. So probably watch the example and then rewatch this portion of the video, and this multi-step process here will make a little bit more sense to you. So let's now do an example of these shunt stubs, well, typo there, sorry, shunt stub calculations. And in this example, what we want to do is we want to match a 25 plus J10 ohm with a 50 ohm transmission line using both a shorted stub and an open stub. So the process is that we determine the normalized load impedance in the same manner that we have in all other examples. We just divide the load by the characteristic impedance of the transmission line material that we're using, and in this case we get 0.5 plus J.2. You can see I've gone ahead and I've marked that on the Smith chart, and I've gone ahead and drawn the operating circle for that. I can find the admittance, normalized load admittance, simply by drawing a line from the center of this, or from the center of the Smith chart to this point, ZL, and then extending it out the other side of the Smith chart, in effect rotating 180 degrees, right? And I find the intersection of those 2 points, and that tells me that YL is 1.72 minus J.68. So what I want to do next is find the intersection of the operating circle with this R equals 1 circle, the circle that's in the middle of the Smith chart. And we can see that there's 2 points, there's that one, and we'll call those YL prime. And those 2 points are going to be 1 minus J.75, that's this one here, and there's another one at 1 plus J.75. And for this matching element, I could use either of those because they both cross the R equals 1 circle. For this example, I'm just going to go ahead and continue using this value right here. So to insert the matching element, what I need to do is move along the transmission line from this admittance point to this admittance point. So I need to know what the wavelengths towards the generator for both those points are. I've already drawn this line here, so I can just read that value right off the scale, and that is 0.2913 lambda. I need to know where this point occurs along the wavelength towards the generator scale. So what I do is I draw this straight line from the center of the Smith chart through the intersection point. I then find where it intersects the WTG scale. I see that that's 0.3462 lambda. So I can determine D, which is the distance from the load to the insertion of the matching element. That's going to be 0.3462 lambda minus 0.2913 lambda. And so I get a transmission line length from the load to the matching element of 0.0549 lambda. So that tells me where to put the element in. So the next thing I need to do is determine the length of either the shorted stub or the open stub, whatever one I want to use. And I just want to make a little note before I do that. Remember that for a short circuit, the resistance is equal to 0. On an impedance basis, Y is equal to 1 over R, and so 1 divided by 0 is equal to infinity. So a short circuit admittance is equal to infinity. So on the Smith chart, the short circuit point on an admittance basis occurs right there, where Y is equal to infinity. For an open circuit, we've got R is equal to infinity, and therefore Y is equal to 0 for an open circuit. And that occurs at that point, the Y equals 0 circle. So the short and the open points flip sides of the Smith chart when you translate from an impedance basis over to an admittance basis. So We've got to keep that in mind when we're doing our measurements. So for a short circuit, what we need to do is we need to cancel out this this minus 0.75 of susceptance here. And we do that with plus 0.75 ohms or mhos of susceptance there. So we've got the plus J 0.75 mhos. And if we're going to do that with a short circuit, we need to measure the distance in wavelengths to the generator from this point all the way around to this point right here. So for the short circuit, we're rotating from this intersection point, which was, or we're rotating from this intersection point, which is y equals 0.25, and we're going all the way to whatever the wavelengths to the generator scale is right here. So we need to draw that line right there, and we see that that intersection point is, let's see, it is 0.1022. wavelengths towards the generator, lambda wavelengths towards the generator. So for the short circuit, we need to rotate all the way from here to here. So that's 0.1022. And that gets me from here to here. But I need to include this distance right here. So I need to add 0.5 lambda. So that's 0.6022 for the short circuit point. So 0.5 lambda, sorry, not 0.5, plus 0.25. I need to rotate from here to here, which is 0.25. And then I need to rotate from here to here, which is that 0.1022. So that's 0.3522 lambda. For the open circuit, all I have to do is rotate from here to the point, and that's just 0 to 0.1022. So the open, just by inspection, is 0.1022 lambda. So the two circuits that I end up with are a length of transmission line of arbitrary length, Z0. I then put a short circuit T line, so that gets a short circuit across it, and then I have a fixed length of transmission line, and then I have my load. This here is D, which we calculated as 0.0549 lambda. And this here is L, which for the short circuit we calculated as 0.3522 lambda. D stays the same whether we use an open circuit or a short circuit, so I can change this circuit to an open just by erasing that, and all I have to change is the length of this piece of coax here to 0.1022 lambda, and that will achieve my matching network for me using shunt stubs, either open or shorted.